Now, as you know, my motive for getting into this began with meteorology. It had to do with the nature of the plasma that I envision is up there in the atmosphere, and this plasma is what forms the basis of jet streams and tornadoes, and those are all involved with what's going on with storms. Now, my notion, though, depends completely upon the notion that if you maximize the surface area of water, you maximize its surface tension. Now, great evidence that this notion is true is just the notion of surface tension in and of itself. And anybody can look that up. You can see that along the surface of H2O, there's something that's harder, something that's stronger. There's tensional forces that exist between those molecules. Now, I looked at that a long time ago and I said, well, it seems pretty obvious that bonds must be breaking along the surface, because a surface restricts the ability of other molecules to complete a situation, because it shoves it into a two-dimensional reality, and so you have a lessening of the ability to complete bonds. From that, I just said, well, wait a minute, if surface tension is stronger and less bonds are being broken, then it's simply a matter of understanding that must be some functionality going on, that the breaking of bonds must somehow have to do with what's activating the source of the strength. And looking into it and finding out that H2O is a polar molecule, I kind of reasoned, well, that must have to do with polarity, but in liquid water, that polarity must somehow be neutralized, and when you break some of those bonds along the surface, that must somehow activate it again. So I realized that I wasn't really trying to figure out why polarity produced that surface tension as much as I was trying to figure out why the molecules that had full connections didn't have hard connections. In other words, why was water so fluid? And the answer had to do with understanding the genuine nature of polarity, and that's the fact that when you complete hydrogen bonds, you neutralize the polarity because you complete the symmetry, and the symmetry is what polarity is all about. Without asymmetry, without it having a lopsided arrangement of connections, there's those tensional forces associated with polarity. And so that's the solution. Surface tension actually does get maximized with the maximization of surface area, because you're breaking bonds. And a really good example of this is the idea of non-Newtonian fluids. Non-Newtonian fluids involves a mixture of water and cornstarch. And what's happening in there is that cornstarch, which has very small granularity, when you put some force on it, it separates some of the H2O molecules, and it separates the weak bonds, leaving the strong bonds behind. And for an instant in time, you have ice. And that's what's really happening with non-Newtonian fluids, is you have ice appearing for an instant. And it's because you separate. It's because you're actually breaking bonds, but not breaking all of them. That's what ice is. That's what's happening with non-Newtonian fluids. And most importantly of all, that's what's happening in the atmosphere under wind shear conditions to produce the very thick plasma, which is what formulates the boundaries of tornadoes and jet streams, and isolates the contents of that under long distances, isolates that contents from the friction of the atmosphere, and allows the pressure of the atmosphere, the differences from one end of a tube to the other, to cause acceleration down that tube. And that is the origin of the high wind speeds we have up high, and that rarely come down low. And when they do come down, it can often be catastrophic, as in tornadoes, which is essentially what a tornado is. It's when the jet stream runs out of water and starts following paths downward, can't find it, eventually does find a very distinct boundary layer of water in the lower atmosphere, this being the water coming up from the Gulf of Mexico, forms a very strong but temporary vortex, which is really what we're talking about here, vortices. And again, wind shear producing that plasma. And that is the vortex that produces a tornado. And once those things get started, they have a certain amount of energy associated with them. They're not going to stop until, they're just not going to stop until they run out of that energy. So that's what's going on with tornadoes also. And that, by the way, is kind of how I got into this. I wanted to understand tornadoes. And this goes back really far. This goes back 25 years when I took a class in meteorology and kind of had a problem. Problem was, I was looking at this notion of convection and I was taking it seriously. I didn't know it was a nonsense notion at the time. I had no way of knowing. I was just a student. And so I tend to take things literally. I look in the book, it talks about convection, it talks about moist air being lighter than dry air. And I did some quick little math on that, and I go, hey, this doesn't make sense to me, and I just, wanted to get some explanation on it, and kind of got deeper and deeper and deeper. I could never get a straight answer. It took me a long time to figure out that they were all just pretending. I didn't know that a whole discipline could pretend to understand something and never quite explain it to me. I mean, who would ever predict that? But that was the case. And that's still the case. If you ask a meteorologist why air rises in storms, let's say you point to a thunderstorm and you say, hey, look at that going up there. What's doing that? And they'll say convection. And that's their whole explanation right there, convection. And I now know that's complete nonsense. There's no convection happening in our atmosphere. In order for there to be convection, you'd have to have situations that we don't have. Now, the real energy, the real origin of the updraft that's happening in a tornado is coming from the jet stream. And it's coming from maybe hundreds of miles away, and it's being delivered in the form of low pressure or high winds. They're kind of both the same thing. I mean, when you have high winds that are going out of your area, what's that going to result in? Low pressure. And so that's essentially why storms have low pressure. And if you think about it, come on, put two and two together here. How can convection, upwelling of warm, moist air, cause low pressure? Why would you ever come to that conclusion? And so when you consider that, you got to consider, well, gee, there's perfect evidence right in front of us that the convection model is wrong, and no one saw it. How can you not see that convection won't produce low pressure? We'll never know, because this is not something that the people in meteorology really think about. It's just, it's like a passage in the Bible. It's just a story to them. It doesn't mean anything. They don't really take it seriously. They don't do measurements. Just the nature of that particular discipline. So I hope you can all learn a lesson from this. Just because someone tells you something is true, it doesn't necessarily mean it's true. There really is a principle in science that truth is a matter of something being reproducible. And that's maybe something you might want to start including in your understanding of science, that reproducibility is what truth is about. It's not about what everyone believes. And you'll find very often in large parts of science that there's just group beliefs, and these beliefs are stuck, and nobody is questioning them. That is a big clue. When you find out that someone believes something, or when you find out that there's a general belief in something, and if you ask, why do you believe that? And the answer doesn't in some way come around to reproducible experimental evidence, you should look at that as a clue. Because that could be indicating that this is just a group belief, and that not only is it not either true or false, but it's just the opposite of whatever you thought it was. And this is big part of science. And there's just a lot of tradition and a lot of politics involved that overshadow a lot of the truth in science. And there's no one going to be there saying, hey, this is what's right. There's no authority out there, the scientific authority, and they're not going to come down and tell you, oh, well, yeah, so what? I mean, think about it. You know, meteorology has been around for over 100 years, and we don't see people in other sciences being upset about the rather obvious fact that their theory is nonsense. Of course, they play their theory down pretty good, so that no one really even knows what's going on in general. And they have a number of different ways of getting people off their tail. But you got to consider, though, I think it's like 170 years when you consider that William James Espy, the person who first developed this notion of convection as being underlying storms, that's when he was looking into this. That's when he theorized this. And yet, 170 years have passed. We had amazing developments in physics and chemistry, and somehow nobody in any of those sciences noticed. How do you explain that? What's going on here? How collectively dumb can people get that it can go on for that long with no one noticing? It's incomprehensible, but yet there it is, and it's right there in black and white. You can go look up in any textbook on meteorology, and you'll see that's the prevailing notion even now. Convection. It's nonsense. There's no steam in our atmosphere, and you need steam to make their models make sense.